So the panel that we're going to have this afternoon is going to be on Terabit POP design, or basically next-gen POP design. And we have three folks that we're going to have present. Doran, Chief Technical Advisor for Ebone, Ted Seeley, Senior Network Architect from Sprint, and Rhonda Silver, Senior Network Architect from AOL Time-Warner. And I think one way to conduct this, or the way that we're going to conduct it this afternoon, is that these guys will each present, and then we'll hold up questions at the end and have a full discussion then. So Ted, want to go for it?
All right, two things I want to say first. I got to be careful there. Two things I want to say first. I'm really hungover, so I'm going to go real fast probably. And Peter Rothberg had nothing to do with the DS3. There, Peter, I told you I'd get even. So obvious things real fast. The space and power issues that we all go through when we go through these giant migrations we're talking about here. Is a big box better or is a little box better? I want to clearly state that we're not advocating either one right now because we don't know what to do yet. How do you make it all work together with your physical infrastructure, your logical infrastructure? And in the future, how do you do this going forward? And the support systems, because they're real important as we move forward into this next iteration of the internet. And what's it all add up to after that? So the first thing, if you're Sprint and you're like us, you have to start thinking about stuff like this about a year out, year and a half out, just from a planning perspective. When you have 8 backbone routers in some of your nodes and you want to migrate all of those to something new, whether it's one big box or little boxes, it's not an easy migration process, and you have to think it through clearly, and you've got to plan way in advance for it. So, like the slide says, migrating, that's not an easy task. So we have two things we can look at here. We look at the big box approach or the little box approach. Not a lot of this is rocket science. It kind of spells itself out pretty clearly. You've got, advantages and disadvantages to both. Obviously the big box will give you less elements in your network to manage, which will give you less elements in your IBs you can manage, which makes things better, supposedly. Hopefully you can add things piecemeal over time, and hopefully things don't consume packet-facing interfaces for interconnection. So then there's the drawbacks there. So if you add one big box and it breaks, you're really, really screwed. Physical infrastructure requirements, I reiterate, they're, space and power are such a big premium. And you might even have to expand existing facilities if you're a big POP or a big carrier and you have limited space in your POPs. So the other thing is it's a huge purchase up front and the risk associated with that. We don't know whether the software systems out there today are designed to do the stuff we want them to do for two reasons. They don't exist.
Ted,
yes, Dave?
speak in the mic more.
They don't exist.
Please.
All right. So we don't know if the software systems out there today are capable of doing this. Therefore, you have this huge risk. So that's the big box approach. And then there's the other box approach, the little box, or boxes as we call them. So this is something that's probably going to be available sooner rather than later. We know that if we go down this approach, we'll never get all of our interfaces on one box. This is something we like to do. It's probably a core-only solution, which means you still have aggregation boxes downstream of these guys. But there are some benefits here. We're already used to doing this. This is business as usual. There's much, much reduced exposure in a failure situation. We probably can add the units piecemeal, but it means now we're eating up customer-facing interfaces probably. But then there's also a chance that it might not happen that way. Odds are it will. It's a risk reduction probably. And there's a cost issue. This might be more cost-effective for us to do in the short term. And there's the drawbacks there. This isn't reducing the mesh again, so this is business as usual again. Probably going to consume packet interfaces again, and if you're a carrier like me, that's no fun. And then there's the scaling thing. This is not buying us anything in the long run, and we'd like to change that. We'd like to see much more time in the network for our boxes in the core than the 3 years we get today. And that's kind of pushing it, actually. So we have to make all this mess work together. We've got 192 and 48 customer-facing boxes. We've got 192 and 48 boxes in the core and the LAN. We've got DPT or SRP in the POP. We've got all these physical interfaces that we have to support as well going forward. which doesn't simplify matters because it also some of them are kind of limited. So then you've also got to look at the large scale, the whole network, and you have, this isn't going to go into every POP. Certain POPs need more box than others. And then there's the other reality that it's going to take an awful long time to do this. It can't be customer impacting. You got to take your time. So you're looking at, I'd really say honestly a year to migrate to anything of this size and scale. Next slide. So you got to make it all work together some more. You only want your core boxes in the mesh, obviously. You only want, your customer boxes around with other clients always. There's nothing earth-shattering here. The issue is growing the network going forward after you started down this path. And this actually ties into the economic drivers. I would tell my account manager over and over, the next time I have to buy more cards to go through an upgrade or to upgrade a switch fabric, I'm going to shoot them. We're tired of doing that, and I'm sure most of the people in the room are as well. Every time I add a box, I don't want to buy 5 cards to pigeonhole that box into the network.
You sound familiar here, but this is right into the mic.
All right, I'll speak right into the mic. The thing is, I have a loud booming voice and it might hurt people's ears.
No, you don't.
All right.
Well, are they from Sprint?
Probably. That's good. So, back to what I said. The thing here is once you go down this path and you make this leap of faith, you want to be able to upgrade these things seamlessly and effortlessly, and and not have to take cards out, move cards around, jockey things around the network, because these are just painful evolutions, and especially when you're dealing with 4, 5, 6 routers at a time. A lot of the people in this room who have those size networks know exactly what I'm talking about and understand what happens when it goes wrong. So moving on, there's the other big thing, the support side of this thing. I call it the 3 S's. It's got to be simple. It's got to be something that NOC can still support when you're done. It's got to be sane. You can't need people who are PhDs to understand how the network routes when you're done. And you got to be able to support it when it breaks. If it takes you 12 hours to fix it, you're dead. Your customers are going to leave you before long. So then you got this other thing. If upgrading it means that you're running 2 separate networks at the same time, you just can't afford to do it because you can't afford to operate 2 networks at once. So you've got all these things that go into this mix that you have to, when you decide how you're going to do this going forward. And so what does it all add up to? So to me, it means you approach the whole thing, the network, as a system. And it's just not about POPs and terabits. It's about the support, the cost, the routing, the physical requirements, the deployment requirements, the economic drivers. Each of the elements above, you've got to be able to justify them to move in this direction. Which then, you ask yourself, what's really going on out there in the world today? Is the model that we pursue the best way to do things? And sometimes you don't know. So then you ask yourself, is it easier to disperse the network? And I say, I doubt it, but some cases it might make sense. So I can hear the volume coming up. So again, when you add it all up, you've got everybody and their brother in this business saying the same thing. We've all got 0 packet loss, 0 latency backbones, and these are all becoming the status quo, right? Well, if you read everybody's material and marketing, that's what they say, right? The competition continues to get fiercer, and the price point's lower and lower. We all know that. So that your margins are shrinking. So then does it make sense to make these big box deployments in the core of your network and continue to backhaul stuff? I say no, because this backhaul stuff sucks. It costs you a lot of money in the long run. So the bottom line in all this mix is it's got to be profitable and make you money. You might have a mix of big boxes in certain POPs where you have the bandwidth requirements, and you might have smaller boxes where you want to push out to the edge to get to the customer. But then this brings in this other thing, this access issue we have today where, high-speed access in the local loop is still not there. So more of this. What are we back to then? We just continue to build the network the same way. The physical topology may change a little bit. The switch fabric might change a little bit in whatever box you're using. But the interfaces are the same. All the vendors are using the same chipsets. The only thing that's different is their internal box architecture. This is never going to change. The goal is to move lots and lots of packets in the core. And, you want to push the intelligence further and further out to the edge. This is exactly what we do today. The only thing that's different is you got to figure out a way to do it and make all this stuff work together and still make a buck. That's what it all comes down to. So, history tends to repeat itself, right? And, it's just like the TDM networks of 15, 20 years ago that deployed, except now we're doing it with packets. And the big difference there is the software. Today we need the same software stability they have in their networks, but we don't have today in ours. And that's what I'd like to see the vendors work on, and that's kind of for this guy right here. So that's all I have to say. One more slide for Peter. Peter, Ion is dead. Stop making fun of it. Okay? Thank you. You're welcome. Questions now? Questions later? All right.
Okay, how's the volume? Good. This is what we do today in real live honest-to-God networks in the real world. This is a city-to-city circuit showing a POP. No battery. Yes, battery, but you can't see it. Anyway, the green boxes on the bottom are all routers in one city, another city, and so on and so forth. The blue boxes are a DWDM system doing transmissions across an intercity span. The red and green smaller boxes are access boxes and so on and so forth. The blue dots, if you can't see it at the back, and you probably can't, are amplifiers, which are just passive equipment along the fiber. Typically in a long city-to-city run, what you'd end up finding is lots of back-to-back connections like the one in the middle. Really, optical budgets these days in terms of equipment which is installed in the field is long haul, but not... Oh, hey, a pointer. Oh, and it works. So you have a duplication of this here and there, and this gives you an opportunity to break out a router if you happen to want to in that city. This leads to a POP design sort of like this. We have the LEC come in and deliver stuff. We have an ADM which does long haul stuff, circuits which are less than wavelength in size, SONET circuits, SDH circuits, and the like. And then we have routers. Bit spaghetti-like. You add more and more routers, you add more and more ADMs, you add more and more directions in which your fiber network is running. It gets very messy very quickly. The trend we're heading towards is less and less long haul and more extra long haul and ultra long haul optics. So we get rid of the back-to-back DWDM muxing in the field for the most part. Some of it will exist as a legacy, some of it will get installed because it's cheap. By and large, what you're going to see is a separation of IP and DWDM into their own fiber pair. It becomes uneconomical at a certain point to have IP consuming lots of colors on a multi-service DWDM network, simply because you have lots of optics translating from one color to another, whereas you can teach an IP router to speak its own rainbow of colors on a dark fiber using ultra-long-haul type optics. So what does this do in terms of growing a faster POP now that we're changing the fundamental city-to-city technology? One thing is that you don't have the rainbow of colors to break out from your DWDM gear into your routers, so you have less spaghetti there right away. But you have two main approaches to dealing with what do you do about getting packets in and out of the city to that rainbow of colors going to the north and to the south and to the east and to the west. There are two main approaches. One is to distribute stuff, another is to centralize everything. Centralize everything, as Ted said, is an interesting approach. You end up building gigantic routers and you bring a lot of stuff into your POP. There's lots of local backhaul, probably quite a lot of equipment needed to groom the equipment up into greater and greater channelized collections of circuits. In the distributed approach, you have interesting issues in terms of where do you put your boxes, how widely do you distribute things, how big does your POP get, and how do you manage it? Essentially, what you're going to find is something that's a hybrid, really. So you have the legacy stuff, which comes in as circuits channelized by your local exchange carriers, and you have city enterprise network or LEC rings or whatever. These are rings of dark fiber running around a metropolitan area with various access boxes around it. For those of you who are seeing two colors, it's not a test for color blindness. It's the fact that we actually do run multiple networks. This is an internal slide that I recycled. It is an illustration of the fact that We, in Ebone, run multiple regional networks as well as our core networks. We use exactly the same equipment. We dedicate one box after another to the appropriate AS and do little tricks with IS-to-IS and BGP in order to make that work. This is what a multi-service ring looks like, with the green now being IP and the red now being either another IP network or a WDM network or a SDH-based network, the yellow being yet another network on top of it. What you end up doing is, rather than using Metro WDM simply because it's expensive, where you have lots of dark fiber, you use individual fiber pairs to run around a yellow ring and a red ring and a green ring, and you pass it through unmolested in some cases. In other cases, you break it out and put equipment in and basically manage the individual strands separately. You can do this with colors as well. So instead of a conduit, the dark lines could be a span of Metro WDM. So you have several virtual dark fibers which are managed in some way or another. Usually it involves the same amount of wiring, just extra equipment to squeeze things into fewer physical fiber pairs running around your metro area. CEN is City Enterprise Network. It's the trendy term in Europe for competitive local access ring. It's a ring of dark fiber running around your metro area. So prediction number one is metro dark fiber is becoming cheap and plentiful. Certainly in Europe this is the case. In Stockholm you can get dark fiber cheaper than you can get ISDN. In other cities this is getting to be close to reality as well. There are a few exceptions and they're growing fewer on a weekly basis. It's unfortunate that it doesn't happen throughout the rest of the world, but that's your problem. I don't feel that we need a PDH or SDH infrastructure at all. I'd like to get rid of ours. This doesn't make me popular with some of my friends in transmissions within Ebone, but the reality is that for doing data services where you're moving around asynchronous packets which are tolerant of real-world internet performance, use the internet. Don't bother going and using circuits. What we'd like to do is to use SRP, which is a ring-based technology which uses, among other things, dark fiber or virtual dark fiber or even SDH channels in order to construct a LAN into which nodes move and extract traffic. It's essentially token ring without the token. It works quite well. It allows us to take advantage of the physical topology, which is largely ring-like in dark fiber networks. You construct it from one building to another building to another building to another building. You cross-connect it in most of the buildings. You pass it through into an SRP interface, one side and the other side, wherever you want to deposit a router. They're suddenly on a LAN. This, frankly, allows us to put interesting boxes into the field. One of them is actually mentioned on the next slide, not on this one. But one of the things that we need to do is to be able to support people who have legacy PDH interfaces, Ethernet interfaces, SRP or POS or other interfaces as appropriate and chosen by them when they were using previous connections to the internet. Getting to the customer is tricky, and one of the reasons why it's tricky, as I said, is that there's a whole variety of different interfaces which they're using now. Traditionally, you have a whole bunch of PDH and SDH gear to groom everything together to make this work, and you have 37 or 38 different varieties of doing Ethernet across a metropolitan area in case you want to use that to talk to your customer. It's kind of ugly to manage, but some of it has to be supported. It's easier to support larger customers because, frankly, there are fewer options for talking to them. When you're looking at a customer who's going to be using gigabits per second of connectivity, you're stuck with gigabit Ethernet or something along the lines of packet over SONET or SRP. When you're dealing with customers who are moving only hundreds of megabits per second, you now run into more and more flavors of Ethernet, the faster flavors of stuff. You have some PDH possibilities as well for customers who are moving 30 megabits per second or slower. And even slower when you get into 2 megabits per second, you're not only into the land of PDH, but there's also DSL, there's cable and wireless and so on. The smaller the customer, the more choices you have available to reach them, but the harder it is to manage all of these choices or any of these choices simply because there are scaling issues involved in dealing with these technologies. So what we did was worked with Cisco, our vendor, to develop a device known as the Brick, which is now known as the 10720. And essentially what it is a small router that has an SRP interface that can talk on a metro area ring, it can talk on a wide area ring, it can talk on a DWDM system, and it can talk on an SDH system or SONET system, and has several Ethernet interfaces or gigabit Ethernet interfaces at the other side. It's cheap, it's flexible, it's a real router, it moves things at line rate, it can do strong policy, and it allows you to offer very easy Ethernet connectivity to the end customer now. Other bricks which may or may not happen would, or of course you could use a standard router now like a 7200 with an SRP interface, could talk PDH to a customer, it could talk some other odd interface like ATM to a customer, and then you're running a connection between your access router, which is living in customer's basement, up to the floor in which your customer's computer room is, rather than running the stuff across town. That is, that your access is in their premises, rather than having to figure out how to use your own or other company's resources to connect their customer premise blocks in one building to your facility in another building or another town. This is a picture of a brick. It's an exploded view. This is, when you actually connect all of this together, you have a nice weatherproof system. The only thing that comes out of it is a few cables to hook up power and your optics, and of course a long octopus cable which goes and delivers Ethernet to your favorite type of patch panel. It's quite a neat little toy. One other thing that is developing in terms of POP design is that you are able, using an SRP style infrastructure where you're using dark fiber rings and then building IP-based services on top of it, to use IP itself to deliver services which some people think are rather surprising. So as I said, there's some 37 or 38 different ways of offering Ethernet to an end user on a metro area basis. Gigabit Ethernet done through WDM, Gigabit Ethernet done via an STM64 channel, Gigabit Ethernet done using MPLS, and so on and so forth. This is a rather ghastly set of approaches to do, especially since they all tend to be vendor specific. The idea with UTI is that you use really what amounts to a tidying up of GRE. It's another X in IP type of tunneling, which is optimized for this kind of thing. And you simply lift the raw frame of your Ethernet out of the controller, wrap an IP header around it, send it across your network, unwrap it by throwing away the IP header and delivering it as a raw frame out to your switch or your other station as a point-to-point link. What happens when you're doing POS or PPP or point-to-point Ethernet over UTI is essentially you have an extension cord between box A and box B. In the middle of this virtual extension cord are routers which do encapsulation and decapsulation, and routers which do mundane things like forwarding stuff around the internet. It is an approach that works. It's quite neat to be able to observe Gigabit Ethernet measured services across a metro area with only two pieces of equipment and some dark fiber, rather than some of the horrors that are necessary for the other 37 or 38 varieties. It's also quite neat to be able to use UTI to build an extension cord from, for example, the Lynx switch in London to Doran Carlson's laptop in Stockholm. He connects to the switch as if he had a very, very long fiber. You know, he can ping, he can do ARPs and so on and so forth. It just works. Again, this is one particular vendor who has pushed out this technology. However, I would expect to see more and more of it as it develops in the marketplace. Simply because it's a clean way of delivering a whole bunch of services, either in a metro area on a distributed POP or across the internet itself. And one of the key ways that we've actually used it in practice is to offer IPv6 services. When somebody comes along and says, well, we'd really, really like to be able to experiment with IPv6, do you run it natively? We can say, yes, indeed, we offer you a connection over a virtual extension cord to a router which is sitting in Virginia, professionally maintained, and so on and so forth. Knock yourself out. None of our routers have to understand IPv6. One router on one side of this virtual extension cord has to be able to do the encapsulation and decapsulation, matched with a router who's doing the encapsulation and decapsulation on the other end. It looks like the customer's router is directly connected to this IPv6 only router sitting in Virginia. And again, it works quite well, and you can't tell other than the RTT. I expect that several other services are going to develop over this. Many of them will be focused on stuff done within a metro area simply because dark fiber is so cheap and plentiful in metro areas that the encapsulation overhead in terms of the extra bits on the wire are completely irrelevant. This is sort of becoming the case in city-to-city stuff as well. However, now you could make an argument that some networks are not particularly well geared towards handling encapsulated packets because you have an MTU problem, or because some networks really are full, even though they shouldn't be. And eventually that will all get sorted out, and this kind of thing will propagate beyond the metro area, which leads to really interesting distributed computation and other possibilities, or building virtual networks. And finally, available technology really drives POP designs. One's theological view really of how the internet works and what it should be composed of, and what control plane should be in there, how tightly it should mimic the old historical PDH or SDH system, or ATM, take your pick, really drives what technologies you tend to want to deploy. Your choice of technology affects how your POP is designed and what you can do with it, and how you see your POP in relationship to your network. Again, a maximally distributed approach, you start beginning to see that your POP is really nothing other than an assorted collection of routers nearby one another, rather than something specific you could point to. Stripping out layers saves you money. Removing things like ATM and MPLS and SDH and even WDM is a great way of removing a whole bunch of equipment and technologies which have to be babysat. This translates into a cost savings as long as you're able to manage a reasonable control plane to handle the distributed system. SRP is one way of doing this. The routing systems that we have available currently today are reasonable for handling most of the rest. Scale really is a killer, and distributing stuff out avoids some killer problems in terms of, as Dave is going to ask us, maybe has asked us, floor loading, local electrical consumption, heating or cooling, and so on are all made less of a problem when you're moving little boxes into the basements of buildings all over town, rather than centralizing ever bigger boxes in one single location owned by you. However, on the other hand, you have a maintenance issue in that now you have to send people out to go and babysit these boxes if they break, as opposed to having people on site handling all of the relevant equipment. On the other hand, you also don't have an LAC involved in the case where you're doing distribution. So there's trade-offs all over the place, and some people are going to make different trade-offs than others. It really comes down to worldview and economics. And that's it.
So, hi, I'm Rhonda Silver from AOL Time-Warner. This is the necessary marketing slide. So I'm going to talk about a project that we started 3 years ago named ATDN. Talk a little bit how it evolved and share some statistics, and then finally talk about some of the concerns we have going forward. So what is ATDN? ATDN is AOL Time-Warner's transit data network. It's basically a private ISP that serves AOL Time-Warner and all of its subsidiaries. All the traffic going in and out of there, going to any of the properties, goes in and out of this network. You could basically categorize networking within AOL Time-Warner as there's one bucket that's primarily focused on all the networking gobbledygook that goes around the many servers that we host, and then the other half, which is focused on what's very similar to what happens in an ISP. It's a wide area network, and that's what I'm going to talk about here. So where did it come from? We started with primarily two main data centers in Northern Virginia, and in those data centers we observed that a lot of our subscribers were sucking a whole lot of content from a lot of other people's networks. So we were interested in trying to make that better, trying to make the performance more deterministic and decreasing packet loss and all this kind of thing. So we developed what's known as the Terapop. And the Terapop basically looked like this. A couple of core routers here, and they had connections to a lot of other routers that we either had direct pairings with or the pairings were directly attached down here into the core routers. This evolved. Oops, I'm going the wrong way, sorry. Into web caching. We realized that we were paying a lot of money for transit at that time, and decided we wanted to lower our transit costs or our bandwidth, so we developed caching infrastructures within the data centers. The next logical step from there was for us to get the web caches closer to our subscriber base, which led to I keep going the wrong way here, which led to an extension of the Terapop, which is how ATDN was born. Here's sort of the first version of ATDN. We created several POPs in North America, in the U.S. specifically, in D.C., Columbus. You can see a few locations there, and deployed web caches primarily from our data centers, but also out on the West Coast, and the Netscape campus. We had some international circuits that extended to Europe, and it's not indicated on here, but we also had extensions over to Japan and Brazil and Sydney, which led to the next version of our topology. We deployed additional POPs in Europe, in Japan, and in Brazil, and increased that capacity, which was originally an OC3 backbone to an OC12 backbone, interconnecting all those locations. We also deployed more data centers with the web cache infrastructures in them to get it closer to our subscriber base in the international locations that I named here. Here's a simplified version of the topology without all the extra lines on it. And this is what we're currently working on. It's an OC192 backbone. Little sidebar here. We, in particular in Northern Virginia and also in the Bay Area here, we realized that we could deploy metro WDM infrastructure to reduce our costs for the multiple OC48s that interconnected with our POPs there and also our data centers. I'm going to fly through these. So there's some stuff about our infrastructure there. So POP architecture, what did these POPs look like as we went through these various stages and as we continue to grow it? Here's a physical layout, bunch of racks, bunch of routers, and all the stuff that supports them. It's not too interesting. Here's what it originally looked like. The two routers on the top labeled BB1, BB2, these are what we call our backbone routers. And initially they had multiple OC3 links that would go out to the other POP locations. And below them were attached additional routers we call our POP routers, and this is where all of our external interconnects would come from. So data centers would attach here, our peers attach here, our remote office is attached here, and then we had basically a meshed infrastructure in between there. This extra POP router off to the side is what we call a low-speed router. We typically have one in each of our POPs where we terminate things that are sub-OC3. So this evolved as our bandwidth requirements increased. We went to OC12 backbone and multiple OC12 interconnects, and then this quickly, wrong way, sorry, went to OC48 interconnects when we got OC48 line cards available to us. More bandwidth availability seems to always precipitate more bandwidth consumption, thus we had an OC48 backbone deployed with multiple OC48s in the intra-POP. You see the pattern, I think. This is what we're doing today. OC192 interconnects, OC192 backbone connections. What's easily expected on the horizon for us is this will go to multiple OC192s for the intra-POP, which will lead to, when it's available, OC768s for the intra-POP connectivity, and of course that's always going to lead to the same thing. You see the pattern that we're going here. Not sure, where is this going to go? We've got OC768 backbone connectivity, multiple 192s. There's multiple 768 intra-pop connectivity. This is sort of where we're going. Not tomorrow, but we'll be thinking about this more seriously in 18 months. At the very least, this time next year, we'll be looking at the previous slide. Down at the bottom here, I only show 3 routers. Typically, our POPs range from 3 to 6 routers. So, some statistics. These are the typical statistics you get from our marketing folks. Not too interesting. Well, I mean, it is to our marketing folks. Here's some additional stats. I'm going to hit a couple of these. Number of URLs per day, 11 billion, and 200,000 per second go over this network. An interesting thing down at the bottom there, I just want to throw out there the number of concurrent streams, and these are audio, real media, MP3, and various other formats. And then 1.25 billion IMs on our backbone. Some component statistics here, number of routers that we have deployed, number of switches, a bunch of interfaces, and then a little blip at the end there about how many variables we have to monitor to gather statistics on all this stuff. So ATDN, it's 36 POPs distributed over 17 U.S. states, 7 countries, 5 continents. We have peering with 175 unique ASNs, about 100 gigabits total peering capacity, about 200 gigabits downstream. This was a cool metric I pulled out of the stats. 1,200 terabits a day, which is kind of cool. Anyway, so what are our concerns as we continue to grow and go in this direction with this architecture? High port density is extremely important for us in a small footprint. We like to be able to take the constrained space that we have for a given POP facility, and when we go to a 4x increase on that, magically creating an additional set of racks to deploy the equipment. If it's twice or 3 times the size of your previous equipment, you're actually going to eat up too much rack space, and you're going to run into problems there. So insertability is very important for us. Form factor, 19-inch rack mounts. Cost, okay, don't need to say much about that. Obviously, it shouldn't be a 4x increase. Excuse me. Power, cooling, weight, these are all very important when we're trying to do an infield upgrade to an existing, what's existing. If you can generally handle some power increase, but if your increase in power exceeds the available power in the building, then that's kind of a problem. Management plane obviously needs to integrate. Here's an architectural point there at the bottom. So in our typical POP topology, having too many client routers, and by that I mean the POP routers on the bottom and the illustration further back, they'll eat up a lot of intra-POP connections. And one strategy, pretty popular, I think, in some vendors today, is to create some cool mesh and connect them all together and make it one big monster, or a mega router. That's what I call it. Single point of failure for the entire POP, one mesh, bunch of different line card chassis and all that stuff. I think it's a great idea, but it's going to need to be proven to have the reliability and the 5 nines or 6 nines or 7 nines or whatever the marketing guys are saying nowadays. When we get there, that'll be exciting, but I don't see it on the immediate horizon for this network. Line rate access with processing is extremely important for us. Core versus edge, we really don't see a need to have a differentiation in the hardware or the platforms there. When we're deciding on the bots, we like interchangeability so that we can take steal parts from our backbone routers and put them into the POP routers, or you only have one set of things you need to spare. There's common support things that you can leverage, which is really good. The main difference for us is, well, on the edge routers, on the POP routers, we may turn on these access lists, but on the backbone routers, you don't necessarily need them on. However, we like it in there. Special microengineering techniques, QoS, MPLS, and all the other stuff. Currently, we try to avoid it by throwing more bandwidth at it. However, someday, I suspect there'll be budgetary constraints, or our rate of bandwidth consumption will outpace the rate of decrease in the cost of bandwidth, which will get us back to the point before, which is have to figure out how to do all this microengineering stuff. Some of my favorite comments here. So I haven't seen a compelling business plan on why to do multicast. So that's my point there. In V6, we've got folks that are participating in the 6-bone, and we'll go there when the industry is ready. And then my final point there is, where's all that traffic going? I mean, this is extremely important. I think there's an itch that's being created there to glean information about your system or about your network, to understand where everything is going, to measure statistics on the rate and those changes in where it's going or the performance thereof. My point is, I'd love to not have to go to a third party to buy something to sniff or to split off some of that signal from my fibers to figure out what it's all doing. It should be integrated in the same platform, the same system. Having a third party box that lunges and does something about data, that's cool, but on the edge, I like it integrated. So summary main issues for us is we're deploying the 192 infrastructure and soon the 768 infrastructure, well soon, maybe in 12 months. Line rate ACL is very important. Flow statistics on accessless hits and misses and all that kind of stuff that helps you do DOS tracking, cool tricks to automate all that. A lot of information there. The small form factor I mentioned, insertability, is very important. And finally, port density. We like lots and lots of ports. So that's me. If you want to reach me, there's my email. Feel free. Peering is there. So thanks.
Thanks, Ron. So are these mics on now? If you could have these 3 mics on. Everything okay, Susan? Closer. So right now we'd like to entertain questions for the panel that are up here. And I guess I'll start off with one question. The theme for the first day that we've had today is security considerations and security considerations in POP design. Would be something interesting to hear. Ron touched on it a bit, but Sean or Ted, what are your feelings on any security concerns of how it integrates into next-gen POP designs or into what you're thinking or planning?
I mean, obvious drawback number one is more boxes means more things to secure. A lot of thought has gone into how to manage things which are left out on people's walls outside their houses or outside their places of businesses or on telephone poles. One way to go about doing this, and in fact the approach taken by the BRIC, is to do only in-band management. So since SRP uses POS framing, which relies upon SDH or SONET framing, if you use the DTC channel of your SONET payload to do your in-band management and keep that as a separate, in fact physically separate network from the rest of the internet, then your risk is pretty minimal in a box which has no access into it because it's welded shut. Of course, someone can go and physically destroy your box or physically destroy the wires or cables going into it. This is a bigger risk than in one location facilities which are extremely dense. The problem with one location facilities which are extremely dense is they make really attractive targets, as we found the other week, unfortunately, and making them redundant can be ridiculously expensive as well. So, there are trade-offs all over the place. It really depends on what you're trying to secure against. Ultimately, if you're trying to keep everybody on 100% of the time with no errors, you have a difficult job no matter what you do. Depending on your organization, a distributed approach or a centralized approach may make more sense.
So that's a really good question. I think everybody on the panel has a different set of criteria they're trying to protect themselves with that. So if you're a carrier and your job is to move package for customers, you want to protect your customer first, obviously. Today, obviously filtering for your customer on the upstream is what you want to do for that. But as you move forward in this next generation stuff, and this is one of my pet peeves, is support systems in these next generation boxes need to be able to do this stuff for you. You've got to have the signature matching capability and pattern matching capability, and the box has to be intelligent enough to know that something's going on that it can do that. So then you've got this problem with the trade-off. So this is going to take, take cycles and horsepower and stuff. So now your ability to move packets, which is really what you wanted to do first, is you're going to compromise some of that, or maybe not. So that's the approach I take. I didn't even go into the ISP useful tools that need to go into these things, because it's just a can of worms. We don't have those tools today on the routers that we get. But I think they have to be on the next generation of boxes. And I haven't seen the level of effort there on the vendors that give it the attention that it warrants. So we'd love to see that built in, to be honest with you. So, and whether the attack is on a customer downstream or on a host of theirs or against your infrastructure, we want you want that alarm to go. You don't want to find out what your customer calling you. You want your infrastructure to tell you. So that's the goal as far as I see it.
Can you make any comments, Ron?
Sure. So I think there's a lot of really neat work being done in the vendor community for understanding and profiling of security threats and security statistics and all kinds of things that'll alert either your NOC personnel or your security personnel that, hey, there's something going on that matches our this is bad criteria, right? And I think what I would love to see is you folks that are actually doing that to get together with some of the vendors who aren't doing it, the hardware vendors who are doing the routing stuff, and not require us to kind of underscore Sean's point, not to require us to deploy a bunch more equipment to do that. It'd be nice to integrate it so it's a single infrastructure, single box. That'd be cool.
Thanks. There's a question there in the back.
Yeah, the question is really about diversity. In talking, Ron, earlier, you said keep it simple, keep it standard. And one of the things that we've seen in a lot of cases, even when there is a standard, one vendor's implementation of that standard, whether it be at the laser chipset level or at the BGP routing level, probably works best with that same vendor's other gear. Looking at the Terabit design, it seems to be a little bit different from looking at the exchange point design, in that a lot of times people go with a single vendor for everything. And I wondered what the panel thought about just how much diversity you're willing to tolerate from a management perspective, and what that means for the kinds of diversity issues that Sean Donnellan brought up earlier.
Ted, why don't you take a whack at that?
Well, that's a lot of questions to try and answer gracefully. I don't even know if I can really answer the question very, very well from a diversity perspective. You're only going to, you can get diverse with different vendors, right, and then you've got the standards issue, but as far as diversity goes from a carrier's perspective, you're only ever going to be as diverse as your physical plant is, and there's just nothing you can do about that. And if, some act of God takes out a building on your physical plant and you thought it was diverse and it's not, that's what happens.
Oh, sorry, I meant specifically vendor diversity in gear.
Vendor diversity. Well, you mentioned Sean earlier, and I thought so you were implying that as well. So you're right. There's vendor diversity and there's vendor diversity issues, and there's vendor A implements multicast different than vendor B, and there's some BGP idiosyncrasies and stuff like that. And so if you have a one vendor network, you're usually assured that stuff will work properly, but that's not always the case either. So the decision for us as a large carrier comes down to what's most cost effective for us. Is it more cost effective for us to manage two vendors and then deal with the headaches that comes with that and the different implementations of the different gear, et cetera, or do we get a better return on our money by just having one vendor dealing with the issues that come with that as well? I think in the upcoming year or two, in the current economic situation, which has allowed us to buy some time on this very subject we're talking about, that's something that a lot of the carriers are probably going to think about long and hard. I'll be honest, Sprint will think about that long and hard. So today we don't have a diversity issue. We're Cisco end to end, and that's it. So I'm probably not a fair person to ask that.
How about Mr. Grace on the end then?
Mr. Grace and Sweetness and Light. I would say that it's very clear to me that multi-homing between vendors is at least as difficult as multi-homing between backbone providers. The question is, why do you choose one versus the other? One of the things that comes up on Nanog all the time is you can multi-home between backbone providers and find out they're sharing the same piece of fiber that gets cut. Oops. So what happens when you're sharing the same piece of code which gets a bug in it? The genetics of a lot of the code out there and a lot of vendors is pretty damn similar, and that's somewhat spooky. To me, software diversity is a bit of a chimera right now, despite the fact that I know the very different styles of many of the people who are writing different implementations. We're still stuck with the same standards and the obvious ways of doing things, and the obvious bugs will fall in, and the unobvious bugs will probably get found in many different places rather than just one. So the question is, if you're a backbone operator, do you want to take the risk of your entire backbone goes down because of a coding mistake done by one vendor, or a hardware problem, or a supply problem, or what have you, versus the possibility of, oops, one fire that you have to fight today is from vendor A, but that fire is dwarfed by the fire later on in the afternoon caused by vendor B's reaction to the change that fixed the first fire. Seen it happen. Ultimately, what it comes down to is that, like with multi-homing, there are trade-offs, there are costs. People will make up their own minds. Like with TED, we are a Cisco-only shop, and there are good reasons for that in my mind. I believe that other networks would differ rather strenuously, and maybe you're one of them.
So, I won't comment on that, but the vendor diversity issue, I think you can divide it into two basic areas, and I think both of you guys covered it. There's an economic issue. Does it make sense economically to do it? But there's a twist to maybe the way you were describing it there, Ted, and that is having a second vendor may, let me underscore that several times, may help negotiate pricing with, your other vendor or your other vendors. But if you look at, well, never mind. So, but then the other side of it is definitely the operational concern there. If vendor A is unstable in this particular amount of time, it's nice to have a second vendor so that you've got some stability, at least on part of your network. Of course, there's always the risk that the instability triggers instability from A to B, and you're totally host. But I guess that's kind of impossible unless you do your own hardware, right?
Also, a final impolite point is that you run the risk of a denial of service attack done by the marketeering people on both sides as they try to out-buzzword one another. That's no fun either.
Is there a question in the back?
Hi, I'm Rachel Warren from Akamai Technologies. I think this is more of a question for Ron. I had to write it down because I couldn't say it. I couldn't memorize it. Why do you think you had a little thing up on your PowerPoint presentation saying that bandwidth consumption would outpace the cost of decreased bandwidth? Why do you think this will happen?
So, first of all, I don't know whether that's going to happen. So I can speculate on why I think it might happen, and that is when you look at maybe the OC768 optics, right? I mean, how much sooner are we going to jump to the next stage and thus have, another surge of bandwidth? So sort of hit that critical mass area of here's your glass. Okay, so maybe you can take it and stick a bunch of lambdas on it and get 16, 32, 128, pick a number of lambdas, and each of them are running at 10 gig or 40 gig or something like that. Okay, now we're there. Then what? Right? So maybe when we get there, we'll have an answer, but what if when we get there, our answer is, well, this is sort of the best technology is going to do for the next so many years, at which point, there's no further optimization, I think, that can be done there, and thus, your costs aren't going to keep dropping. Does that answer the question?
Well, couldn't they just, up the bandwidth cost so much that, because once you get to a certain point, if there's more people than there are bandwidth, you can up the price so much. And I forget what my question was going to be. But you might not have that problem if you just up the bandwidth cost so much, I would imagine. If I made any sense.
Sure. So that's a kind of a marketing or economic twist to it, right? As the provider of the infrastructure, you can increase the cost in it. And guess what? You just did what I said, which is you lowered or you decreased the rate at which it was dropping, right?
I'm not good with speakers.
So that would happen too. Thanks.
So I have a question for the three of you, which is on protection restoration and disaster strategies as well. The three of you kind of mentioned that a number of technologies, IP technologies, to be employed can help you, of course, with the protection restoration, but there's a number of technologies we heard about earlier today, whether they be MPLS or various other optical devices to help build data networks to help you protect and restore after various types of catastrophic cases. Do you think this changes at all the type of technologies that you're going to employ in the next-gen designs or that you're beginning to investigate?
Sweetness and light. To be impolite again, please see previous comment about denial of service attack by marketeering-oriented people with respect to protection mechanisms. IP routing works reasonably well for applications which realize that there may be multi-second outages in the real world. Oops. Applications that can't deal with it either need to adapt, be rewritten, or be replaced by something else which offers similar functionality. Anything else, like trying to make the internet work faster, switch in microseconds from one path to another, is just simply a pipe dream done by people who have nothing better to do than to try to say, hey, we have the solution and they don't buy from us. So the reality is that we don't have solutions to do this kind of thing. What we do have is IP routing, which works reasonably well when your topology is sane, even when it's not so sane. And we have restoration technologies which are available at lower layers. In layer 2, you have the failovers that you get from SONET or SDH when you're doing 1+1 protection. You have similar protection PDH layers. You have the ring wrapping done in SRP. You have partition healing and other LAN technologies and so on and so forth. The combination of all of them gives you a trade-off between adapting to a change in topology or forcing a constant topology in the face of actual physical or logical changes to the underlying network gear. We play with this stuff all the time, and I don't think that there is any magic point at which you should say restoration should be done here. The topology should always look like this because we have a layout of XYZ tunnels, XYZ circuits, you name it.
All right, my turn. So the reality is when you have customers on your network, it always breaks. It's the tail circuit going to them. Okay. Everything is delivered end-to-end on SONET services almost exclusively in America. They're a little different for Sean. Again, my problem is different from Ron and Sean's. So just to be kind of brash, a traffic engineered tunnel over the customer's T1 does him no good when some stupid bellhead tech in the CO lifts his copper pair. Okay? Right? So that's 99% of the problems that customers encounter. The circuits delivered on SONET services protected end-to-end today. That's standard. The core of the network is completely redundant. Case in point, Baltimore tunnel fire, we lose 11 OC-48s, don't drop a single packet. The network works just like it was supposed to. No fancy, hand-waving technologies and stuff like that. So I think if you just build it soundly and you do it the right way, and you don't compromise cost for the expense of your customer service, and you give them these SLAs that say 99.99% uptime or we pay you back, it's kind of a simple equation. It means you have to do it right. So that's kind of how we do it. Everything's diverse. Everything's physically diverse. It's logically diverse. There's two of everything. We're a carrier, okay? So we build the network like that. So I don't think, like I said, it doesn't help the customer when it's his copper pair that's lifted and that's why he's down. That's,
Yeah, Ted, true, but I mean, I have enormous respect for SprintLink and the way you continue to do things there, but are you saying that multi-second outages never happen? Routers never crash?
Well,
Failures never happen?
no, I didn't say routers never crash, but so when the router crashes and those sets of wide area network links go down, there's a whole another set there on another router that hopefully is still up. Okay, so it's a cycle time between those crashes, right? You just hope they don't happen at the same time. All right. Ron?
One second. Peter, is that you back there?
Yeah. Routers crashing is actually a good thing. I think they should crash more often and longer, because that way we ensure we have a redundant network.
I can't, I couldn't hear you. What did you say?
Do you want me to
Routers should crash.
Peter believes that routers crashing is a good thing because this encourages the development of redundant networks.
Ron, did you want to make a point?
I guess one different perspective I can add to the, go ahead, is there a comment?
Yeah, I just want to comment that I think SLAs with 3, 4, 5 nines is a bunch of marketing BS.
No, absolutely. Agree.
I don't understand why we're addressing that. In the industry, I mean.
Why are people in this room asking for X% uptimes when they're buying services from people like us? We will sell you what you want, honest.
Exercising failure and observing that redundancy works is good, but having all of your routers crash because of a single packet that triggers a bug in your major router vendor's software is a bad thing, because then none of your circuits are up.
Yes, thank you for that insight.
Ron, did you make a point? So, Ted, I've got to ask, is ATM dead?
Yes, Dave, ATM is dead, all right?
So the point carrying further is, Sean presented that Ethernet is king, and you're presenting that ATM. Oh, sorry, you mentioned that Ethernet services can be delivered to customers, and Ted, recently your company has changed its service offering. Are there kind of related back to new and interesting technologies and services that can be deployed? Does this now open up Sprint to new and interesting services that can be deployed?
So it's a real good question. So so the truth of the matter is the service delivery options in Europe and the service delivery options in the domestic U.S. are 180 degrees out of phase with one another. All right. So over there, people can put fiber in the ground and have done so quite liberally. Over here, when people put fiber in the ground, they do it as a collective little coalition, and they all lay fiber down the same street together at the same time, and so you've got a wonderful amount of fiber within like this one street wide width. Go a block off it, no fiber. And they all build to the same bright, shiny, tall buildings. So you've got real diverse service offerings there, right? So, I don't know. So there's some interesting work being done in the ITF, or Ethernet over copper, like T1 type servers and stuff like that. That might change it. I mentioned it in my talk. There's an access paradigm shift that needs to happen here in the U.S. for that to happen. And there are an awful lot of telephone companies that make an awful lot of money with today's model the way it is, who, they don't want that to happen. They like their copper plant that's paid for 500 times over that they charge you $32 a month for, right? And until that changes here in the, I'd say no. It's not something you're going to see an awful lot of. You'll see pockets of it. You may see, like Ron's company, they've got access to cable plant and they can use that. But it doesn't hit the majority of the market in the U.S. It hits pockets. Does that answer your question?
Sure. Ron? Your company?
What was your original question?
Basically, it was the change in service offerings that are now able due to technology changes, and how that's going to affect your next-gen design.
I thought it was about Ethernet.
That's one service offering that could be made.
Yeah, so I think some exciting service offerings from my perspective have been the advent of Lambda services. In some situations, it makes sense to buy dark fiber, but when you do the economics, sometimes there's no break-even point there anytime soon. So you need to consider point-to-point from point A from your two different pop locations. Sonnet looks typically very unattractive, and there's some really nice efficiencies available in a Lambda service, and I like that because then, in some cases at least, you can frame it with whatever you want, whether it's Ethernet or Sonnet or whatever you stick on your end of it. Not all Lambda service providers do that stuff, but some of them let you do whatever technology you want. That's cool.
I just want to say one more thing. I'll probably be fired now for making fun of those phone companies that charge $32 for copper pairs, by the way.
Well, I won't be. Our CEO likes to talk very, very harshly about the fact that, for example, in the United Kingdom, which is occasionally considered part of Europe, last year the number of copper local loops which were unbundled amounted to 37 total. This is in a country of some 50-some-odd million people. It's not uniform across Europe. There are places which are lucky, like Stockholm. There are places which are unlucky, like the United Kingdom or Ireland or what have you. Really, what it comes down to is there a will on the part of everyone involved to try to solve the issue that the lines going from people's houses all go to facilities controlled by former monopolies or existing monopolies? Yes, no. If the answer is no, there's no will to fix this, the new services will be a long time in coming and will trickle down from the people who can afford it or who are lucky to live in certain areas to the people who are less fortunate. If the answer is yes, then indeed broadband to every single household is an interesting possibility. Who knows what the hell happens then?
So all three of you mentioned power weight cooling in different physical dimensions that are required of the devices, as well as increased port density and increased capacity of your networks. Sometimes those the goal of decreasing the amount of power, weight, and cooling required and the amount of port density that can be put into a POP are almost at times mutually exclusive, or at least certainly competing. How is this going to affect how you're going to put it in and make the decision, put in new devices in and affect the decision of whether or not to go centralized, distributed in your next design and splitting across potentially physically diverse buildings and having now a distributed POP as well? Sean?
Okay. The origin of Ebone and Hermes Europe Railtel is separate companies which got mushed together into a company then called Hermes Europe Railtel, then called GTS, and then separated out again and called Ebone, is the fact that there were several companies, each of whom had a facility or two facilities in any given large metropolitan area, only big enough for their own stuff. Having lots of small facilities scattered around a city like Frankfurt or Munich or what have you forces you into doing distributed stuff from day one. So in a sense, we were kind of lucky in that, well, we had to make it work from day one. In a sense, it was very difficult for us to investigate the idea of moving into really big facilities and staying there. Europe also really doesn't facilitate that unless there happens to be on Mars relative to a major city, simply because of the density of population. When you're looking at suburban Virginia, you're looking at a really different environment where space is quite cheap. There's lots of people to maintain that space. There's lots of power around and so forth. Maybe your answer is a little different in California last summer versus this summer. Who knows? So I guess it's going to depend on the overall environment, both of the company and of the place in which they're operating.
Okay. So I also alluded to that in my slide, like you said. Being a facilities-based provider, for us, if it's in our roadmap going forward in our plans, then we build accordingly to support it. It's a time issue and a cost issue, and it comes down to which of those sites truly merit something of that size and scale and magnitude if you go down that path. So you have to make that decision up front well in advance before you take that plunge. I think it's going to be a combination of both. I think, as I stated, you got to push out closer to the customer, reduce your capital costs and backhaul, et cetera. And at the same time, you've got core nodes where you've got too much traffic that you've got to forward and route that require these kind of boxes that we're talking about. So in those facilities, you've got no choice. You've got to bite the bullet. I can't just say, all right, when the 8 routers in this site are done and I can't add any more, I'm going to turn it off, or I can't move it. I've got to augment what's there, if I'm committed to staying in the business. It's pretty cut and dry.
Ron?
So, power, cooling, and weight, right? So it's funny. I'm thinking of an example. I think of some space that we were in where we did an upgrade, and then we later found out, and by the way, because of weight constraints, you have to, put those devices only in X number of rack units in proximity of each other. You can't have, so many. And so, anyways, that's very important for us. When you look at all three of those factors, if it's going to take another a couple more cooling units and there's no space to put them, or that space is going to eat up your colo availability there, then that's a showstopper, right? Because if the device is too heavy, it's going to eat up. It's too hot or draws too much power. You have to move it to a new location, because I'm thinking that if that location's out of any of those resources, the expense of building the new POP is it's more than just moving the equipment to a new location. It's all this infrastructure that's probably already there, the dark fiber that you may have procured into that building, the peerings that might be terminated into that building, all that stuff. It becomes very expensive to just find a new location. So those are very important.
Question in the back.
Yes. I'd like to ask the entire panel if you've had to deal with questions as to what layer of the network to rely on for resiliency. In other words, if you've got an optical switch that gives you maybe 4 different choices, 4 different levels of automatic reconfiguration, what your thinking has been, whether, do I rely upon layer 3 versus the highest possible layer 2 resiliency, or do I go with a lower level of automatic reconfiguration at layer 2 because I know I can rely on my IGP?
I think I'll start that if you guys want. I think as an engineer, you have to look at all those factors. You can't micro-engineer a POP and then have your entire enterprise go down when that POP loses power, right? So you have to look at it by component, and then also on the system level. So if you're considering a point-to-point link between one of your backbone routers in POP A and another backbone router in POP B, if you've got diversity there, that's good. So when you bring up your second link, is it that important that you have diversity? Well, okay, they're on 2 different paths. You've got physical redundancy, great. Now you have to look at the next layer, which might be the layer 2 component. Is the SONET that important anymore? If it's a SONET frame circuit, well, not if you've got 2 of them, but if you have one, you might have to look at implementing linear APS. If it's very critical for that circuit to always be up. But that introduces all these operational problems with managing linear APS circuits and all that junk, but I won't get into that. And then finally, you have to look at the layer 3. If you lose that IP path in your IGP, what happens to your entire topology? I don't think you can say one is more important than the other. You have to consider all those different layers at each part of your network, and then on the entire enterprise.
So 2 things there. One is really standards there, because you mentioned optical cross-connect or an optical switch. So there's no real standard there yet for that today. I mean, how many short-reach OC1 and 2 standards are there proposed right now? Some of them aren't even capable of traversing an optical cross-connect. And the other issue, and Sean's slide showed this in his DWDM at-drop capabilities, the optical cross-connects out there today have a very limited amount of express traffic capacity and at-drop capacity. So it's kind of an immature technology as I see it. A couple of years out, it may not be. So for Sprint, we just use the DWDM plant that's in place today and use it physical diversity approach and use layer 3 for our protection. We have no more SONET infrastructure in our backbone. although all of our customer circuits are all SONET protected until they hit their target router. So and as Ron said, you kind of have to look and evaluate all three, but then you also have to look at what your options available are as far as your physical plant and your capability there and what you can and can't use. And you're always going to be a slave to your routing protocol, right?
Well, I'm in two minds about this. In one sense, Ron is right. You should do it at every layer possible, and make a choice about whether in this layer it's cheaper than in that layer. However, if we're going to start taking the clean separation between OSI reference model layers and treat those drugs pretty seriously, then you sort of want to ask yourself, why is it that any given layer N is going to make any assumptions at all about any layer N minus 1? Well, in OSI land, they had the connection-less and connection-oriented service, which offered different reliability guarantees and so on and so forth. Applications should really be take a universalist approach to what they're willing to talk to one another across in terms of performance, in terms of reliability. Yeah, you can lean on TCP and say, yeah, TCP is going to deal with all of this except for maybe a long-term outage, a persistent routing loop, a crash at the other end, you name it. You could also take the approach just as easily that why don't we leave it to the application, like LukeMFTP, done by some of the BSD projects, which goes and does aggressive restarts and tries to resume the download of a file even if you have a long-term outage caused by something that none of the other layers can cope with. I think it's an application-by-application decision whether you're going to think that everything that's given to you already is sufficient or whether you have to add something new in for extra resiliency.
What do you think? Do you have more?
Nope, there's no more questions. It's a lot of fun.
Yeah, thank you so much.